Howdy, partner. Welcome back. I am a cowboy, really, I promise. And I didn't think about that because now I've got hat head. Anyway, in the last video, we talked about how if I were to take 10 of these slips of paper that were originally in this hat and draw them with replacement, and I got 2 out of 10 that had 1s on them. All the rest had 0s. And we're trying to estimate how many 1s, or the proportion of 1s that are in this hat. And we said, well, just by taking one sample of 10, the best guess would be that the proportion of 1s in this hat is 0.2, because that's what we got in the sample. But only taking one sample of 10 seems like not very much. So we ran a simulation and determined what the sample proportions among all the samples would look like if we did 10 slips with replacement 100 times, 1,000 times, or 100,000 times. And we noticed that the more times we take 10 slips out of the hat with replacement, the more unimodal and symmetric this histogram becomes. Dare I say even approximately normal in shape? And that's an interesting point. So I want you to see that there is a difference between making a histogram of individual data values and these histograms. The data that are making up these histograms are not individual data values. They're not whether an individual slip of paper is a 1 or a 0. The data values here are sample proportions for samples of size 10. So when I say that this histogram represents 100 trials of 10 slips, what that means is these frequencies add up to 100, but each of those 100 things are a proportion from a sample of 10. So it's important to recognize the difference between individual data values being graphed and what we have here, which is sample proportions being graphed. This represents 100 samples, 1,000 samples, 100,000 samples. All right. So we can take 10 slips with replacement each time as many times as we want. Or we could do something else. Let's see if this works first try. Okay, so here we have 1,000 trials of 10 slips. This was the second histogram. Essentially, we're doing the same thing. So this is 1,000 sample proportions, 1,000 p-hats. And you can see that the shape, fairly unimodal and symmetric, approximately normal already. We didn't have to necessarily take 100,000 of them. But instead of taking more trials of 10 slips of paper, what if we take 1,000 trials of more slips of paper? Instead of just 10, what if we took 100? Interesting. First of all, you see there are more bars in this histogram. And that's because if you only take 10 slips of paper, your only possibilities for the sample proportion of 1s are 0, 10%, 20, 30, 40, 50, 60, 70, 80, 90, 100. When you start taking 100 slips, you can have anything from 0% to 100% by 0.01s. So that's why you're seeing more bars here. But I also want you to notice the scale of this horizontal axis. Here we go all the way from 0 up to 0.8 or 0.9. But look at this scale. The smallest is 0.25 and the largest 0.55. This is a much narrower scale. Why is that? Well, when you're taking 10 slips of paper, it's fairly easy to get something that's kind of strange. Like getting 2 out of 10, not unlikely. Getting 7 out of 10, it's not going to happen too much, but it can happen. When you start taking 100 slips of paper, it's going to be a lot harder to get something like 20 out of 100 or 70 out of 100 if that's not what the true proportion in the hat is. And you can see here, we're coalescing It looks like the center is around 0.4. Let's keep going. We've done 10 slips, 100 slips. Let's do 1,000 slips. Maybe you can guess what this histogram is going to look like. What are some of its features? What's the shape going to be? Where is it going to be centered? How big or small is the spread going to be on that horizontal axis? Right. Same basic, normal, approximately normal shape. And our axis here now goes from 0.36, or maybe a little bit below, to 0.44. So even tighter than this, right? It's going to be very difficult for the number of zeros and ones that are in the hat. It's going to be very difficult to get anything outside of anywhere from 36% to 44% of ones with a center around 0.4. Maybe you're starting to see what the proportion of ones in the hat was. Let's do one more. 100,000 slips of paper with replacement 1,000 times. Of course, it had to give me something kind of strange there. It just looks like it's a little off here. Still relatively normal, approximately normal shape, unimodal symmetric. Look at the scale of this axis. From 0.394, and we could say over here is 0.406. I think we can say with a high degree of certainty what the proportion of ones in the hat was based on this. If you took 100,000 slips of paper with replacement 1,000 different times, this is what the sample proportion of ones looks like. It looks like it's centered around 0.4. And to give it away, yes, there were 100 slips of paper in the hat originally, and 40 of them had ones on it. When I took one sample, I only got 2. But if we take 100,000 slips of paper with replacement 1,000 times, we can see, not necessarily with certainty, but pretty darn close to it, how many ones and the proportion of ones that are in that hat. So there's power in taking repeated samples from a population. And I'm not necessarily saying that that's something that's practical, but in terms of running a simulation, it can be really helpful. So we're going to get into what it means to take all the possible samples of a certain size from a population. So there are 100 slips of paper in that hat. You could theoretically take every possible sample of size 10 from the population of 100 slips. Some of those samples of size 10 have no ones. Some of them have 10 ones. But the shape that you're going to see is probably close to what you've got here, where it's going to be a roughly normal shape. It's going to have a mean proportion that is equal to the population mean. And the more of a sample size you take, the smaller your spread is going to be. And this is the foundation for this entire unit. If you take all the possible samples of a given size from a population, that's what's called a sampling distribution. Okay, so this is what we have determined here. The distribution of all the possible values of a sample statistic, and this applies to any sample statistic, proportions, means, medians, IQRs, standard deviations, ranges. You can do this for any statistic. The distribution of all the possible values of that statistic for samples of a given size. So the sample size has to be the same for all those samples. That's called the sampling distribution for that sample statistic. So a sampling distribution is a distribution of sample statistics, not a distribution of individuals, which is what we've been talking about in the past, but a distribution of sample statistics. So in this particular case, what we just did with the slips of paper from the hat, if we were to take all possible samples of 10 slips from the population of 100 and calculate the sample proportion, or the p-hat, for each of those samples, we'd have a bunch of different p-hats. We could construct a histogram similar to the ones that we saw from the simulation. We can view the sampling distribution of those p-hats with a histogram. Now, the histograms that I showed you a few minutes ago are not the sampling distribution of p-hat. Those were just simulated results. Some of the samples may have been the same exact 10 slips multiple times, and there were probably some samples of size 10 that weren't included in those simulations. But the sampling distribution is all the possible values of the same size, all counted once. But I think the main thing students get confused about with sampling distributions is they're used to, when they see a histogram, thinking that that is the distribution of a random variable, of individuals. A sampling distribution is a distribution of sample statistics. So in the case that we just did, each of the things building the histogram is not an individual, but it's a sample proportion. And we're going to see in this unit sampling distributions for proportions and for means. We're going to leave all the other statistics for a separate course. But as we go through the unit, I want it to become clear. Sampling distributions are distributions of statistics, right? It's built by taking many samples. What's so interesting about sampling distributions? Why do we care what the distribution of a bunch of sample proportions are if we took a whole bunch of samples from a population of the same size? Well, it turns out these distributions of these statistics allow us to more concretely try to explain a population based on a single sample. And we'll start answering questions like that in the next unit, but we really have to nail down what these sampling distributions are and how we can model them. So just as if we were dealing with the distribution of a random variable of individuals, we want to assign some of the models that we've been talking about to these sampling distributions also. But these sampling distribution models, first of all, they require independence of individuals. If the individuals from the population aren't independent, the formulas we're going to be using for the standard deviation and variance in particular are going to be problematic. So in order to be able to say that we have independence of individuals, we need to meet a couple conditions. Being able to assume independence of individuals for a sampling distribution requires two conditions, and the first of which is there has to be randomization involved. And randomization looks different depending on whether your data comes from a survey or an observational study, or whether it comes from an experiment. If it comes from a survey or some other type of observational study, the data has to come from a random sample. If it doesn't, you can't assume independence of individuals, and the formula for the standard deviation and variance falls apart for these sampling distributions. So you have to have a random sample, or if your data comes from an experiment, you don't necessarily need a random sample, but the treatments need to be randomly assigned to the experimental units. So we're getting back into Unit 3, the difference between observational studies and experiments. The randomization for an observational study is in the sample itself being random, and an experiment, the treatments have to be randomly assigned to the experimental units. The other condition that must be met for you to assume that individuals are independent for a sampling distribution is our friend the 10% condition. And this is only if you're sampling without replacement. So for example, for the slips of paper in the hat, if I had taken out a slip of paper, put it off to the side, and then taken another slip of paper, that's sampling without replacement. I didn't put the first one back in. If you sample with replacement, then automatically you've got independence of individuals, because the probability of getting a certain type of slip of paper would be the same each time if you replace. But if you sample without replacement, you must sample less than 10% of the population. Otherwise, as you keep taking individuals out of the population, the probabilities change. But if you sample less than 10% of the population, the probabilities of certain events don't change very much, and we can assume that those individuals are independent. So you need to meet both of these conditions in order to assume individuals are independent, so you can use sampling distributions. So I brought our histograms back up for when we ran our simulations. And again, these are not the sampling distributions for the sample proportion in the slips of paper in the hat, but they provide a useful, facsimile of what the sampling distribution might look like. What shape did we say that these were approaching, especially as we used more trials or had a bigger sample size? They're getting close to a normal model, right? We can say that these models are approximately normal. So, it turns out that's the model that we want to use for the sampling distribution for sample proportions. But in order to use this normal model, in order to call the distribution approximately normal, there has to be a condition that's met. It's not automatic. What I showed here had fairly large sample sizes or many, many trials. Here is the condition you need to meet in order to use this model. It's called the success-failure condition. To be able to use an approximately normal model for the sampling distribution of sample proportions, your sample size needs to be large enough. And to check that, we're going to check what's called the success-failure condition. And oops. It's actually two different pieces. They make the condition together. Whatever n is, which is your sample size, if you multiply that times the probability of success for whatever your variable is, that product has to be at least 10. Also, the product of the sample size and 1 minus the probability of success has to be at least 10. If either of these is not met, this condition fails and your sample size is not large enough for this to kick in. So to give some examples of the success-failure condition in action, let's just suppose that I want to take a sample size of 30 from a population. I'm not giving you any more context than that. It doesn't matter what the variable is. We're just checking this condition, just see how it works. And let's say the probability of success for this variable is 0.4. If we were to check the success-failure condition for this value of n and p, we would get this, 30 times 0.4 and 30 times 1 minus 0.4, which would be 0.6. This is going to be 12. This is going to be 18. Both of these numbers are bigger than or equal to 10. So for this value of n and p, the success-failure condition is met, and if we wanted to, we could model the sampling distribution of sample proportions with an approximately normal model. We would use the normal model, but we would call it approximately normal. Right? But let's change it up and say that n is still 30, but the probability of success is now 0.95. That's a very high probability of success. Let's see how it affects this condition. We take n times p. It's going to be 30 times 0.95. That is 28.5. Let's then take 30 times 1 minus 0.95, which is 0.05. That's only going to be 1.5. Remember, both of these have to be at least 10 for the condition to be met. This one works, but this one doesn't. So what you have to watch out for with the success-failure condition, yes, it's a measure of having a large enough sample size, but just because n is large doesn't necessarily mean this condition is met, because the closer p is to either 0 or 1, the higher a sample size you need for these products to be large enough. So I want you to get comfortable now that we're talking about sampling distributions for sample proportions. if you're ever asked to calculate probabilities based on a sampling distribution for sample proportions, you need to check these two conditions to make sure that your individuals are independent, and you also need to check this condition before you can use the normal model for that sampling distribution. So maybe you're like, Mr. C, I appreciate the fact that these things called sampling distributions exist. I'm still pretty confused about what they are and how we can use them, but who cares? Like, I don't see the point. Can't we just go back to distributions of random variables from individuals? No. One of the reasons sampling distributions are so important is that they allow us to see the effect of sampling variability across samples from the same population. So in the past, we have taken samples from a population and we said, hey, p hat for that sample is whatever. Is that a true reflection of the population? It's hard to know from just one sample, right? That's like taking my one sample of slips of paper from the hat and saying, well, my sample, it was 0.2. Does that mean that's what's in the hat? Only by looking at the sampling distribution can we put that single sample proportion in the context of all the possible sample proportions we could have seen to say, is that likely? Is it unlikely? If so, how likely or unlikely? So if we go back to what we talked about at the beginning of the unit, Mr. Binkard versus Mr. Jones teaching trig, we said we took a sample of students from each of the teachers, and the sample proportion of grade among Binkard's students was an 83%. So students in his class, on average, from that sample got 83% of the points. But with Mr. Jones, that was 76%. And we want to know, is this enough evidence to suggest that the two teachers are different, or that Mr. Binkard is somehow better than Mr. Jones? Maybe he's a better teacher, maybe he just grades easier, maybe he gives easier tests or homework or whatever, right? And it's very difficult to tell just based on this whether that's true or not. We need some more information about the population. And this is where sampling distributions come in. Because the difference here could be due to the students that each of those teachers have. Maybe Mr. Jones's students are just not quite as good as Mr. Binkard's. I think it's random how students are assigned, but who knows, right? Maybe something weird happened. Okay? So how can we possibly account for that difference? Well, we could run a simulation, like I showed you with the slips of paper, using that computer software. You could run a simulation where all the students in both of these teachers' trig classes are randomized. You take all the trig students and you randomize them to either have Binkard as a teacher or Jones as a teacher. And as we're doing the simulation, we're assuming there is no difference between the two teachers. We already know each of these students' grades, so those students and their grades either go to Binkard or Jones. If we assume there's no difference, that shouldn't matter. Okay? What we can do then is take random samples of the same size for each teacher now that the assignments are randomized, and we can look at the sampling distribution of the grades for each of those randomized class lists. And we can come up with a sampling distribution, a histogram of those grades, and we can see where do Binkard's students end up if they're randomized? Where do Jones's students end up if they're randomized? The difference here is 7%. So if we take the sampling distribution for Mr. Binkard's randomized students and for Mr. Jones's randomized students, for all the different possible samples that we could have, how likely or unlikely are we to see a difference of 7% in their scores? If that's not a very likely occurrence, then maybe we can start to say there is something going on between these two teachers. But if what we see is that those students have very similar scores, and this is like an outlier, then we might say, well, this sample was just strange The two teachers seem pretty similar. This was just a weird sample for some reason. Okay. So sampling distributions allow us to get some context in terms of how likely or unlikely is it to get a sample proportion of p hat for this population or for that population. I want to bring back these histograms from our simulation earlier to make a point a little more clear. I said these did not represent the sampling distribution of the sample proportion of ones in the hat. And that's because, like I said, a sampling distribution is very specifically all the possible samples of a given size. There was no guarantee that we got all samples of size 10 in any of these models. And even if we did, some of them were almost certainly repeated. These are not sampling distributions, but they are randomization distributions. So these are where you have a collection of sample statistics, so sample proportions in this case, generated by simulation, assuming known values for the parameters. The parameter in question here is what was the population proportion of ones in the hat overall. And if you were eagle-eyed and you know how to code, you might have noticed that to generate these randomization distributions, I assumed that the population proportion was 0.4. And that's why you see all of these distributions centered around 0.4. They're not sampling distributions because they're not exactly every possible sample of size 10 counted once, but they do have value, and you can simulate what a sampling distribution might look like by generating these randomization distributions instead. So that's all I wanted to talk about today. You've learned a lot in this video. We talked a little bit more about this randomization distribution, and now you know that's what it's called. We know that there are these things called sampling distributions, and specifically so far we've been talking about sampling distributions of sample proportions. And that is where we take all the possible samples of a given size from a population and we look at what that looks like. We've seen that in general, we see an approximately normal shape for those sampling distributions. That's going to be the case no matter what statistic that we're going to look at and no matter what the population looks like, as long as you meet certain conditions. You also learned in this video, in order to use a model for the sampling distribution, you have to have independence of individuals, which is determined by randomization, either a random sample or random assignment of treatments for an experiment. And what was the other thing? Oh no, I forgot! What was it? Randomization and the 10% condition. That's right. If you want independence of individuals, you have to sample less than 10% of the population. And then in order to say that the model is approximately normal and be able to use the normal model, you need to meet the success failure condition, which is that n times p and n times 1 minus p are both at least 10. That condition is specific to when you're talking about sample proportions, because we've got p in there. We're going to also be talking about sampling distributions for sample means a little later in the unit. That's going to have a different condition for a large enough sample, because you won't have p when you're talking about sample means. But we'll get to that later. But we've learned a lot so far, and I can't wait to see where we're going. Well, I know, but you don't. With these sampling distributions, it might still be pretty fuzzy what it is we're talking about. Once we get into some more information, some background, and then start going through some examples, I think things will start to crystallize. But this is your introduction, and I hope it helped a little bit. So we'll see you in the next video.